All right. Hello, everyone. I hope you're doing fine. This is day 29, and we are going live from with Ingersoll Machine Tools, and I'm just waiting to have a validation that we are live on LinkedIn and this is working. And I got the confirmation, so that's awesome. Chris, how are you doing?
Doing good, not too bad.
Awesome, awesome. So usually the way it starts is I give a couple of minutes for people to receive the notification and to log in. Although this is like it's set to start at 12 noon, very often I start like a couple of minutes early, late, just to make sure that the system is functional. So let's go ahead and get started. I can see already several people saying hello, hello Pignon, hello Venkatasan, hello Elio, and I see the numbers spiking up, which means we are rolling. And by the way, before I let you introduce yourself, this is the first time ever that I'm trying to broadcast on the LinkedIn. Obviously, this is where I have, but Chris, especially knowing you're not a big fan of social media, you're also on my YouTube channel, my Twitter, and my Facebook channel. So here we go.
All right.
Full,
So I think at this point I'm supposed to say something like, please subscribe and smash that like button or something like that.
that would be great if you say. I've never done that. The whole actually, people are already subscribed because. But you know what? If someone is watching it that never seen it before, that's a good thing to say. All right, so I'm gonna go ahead and get started. So I'd like to start with you introducing yourself and telling us a little bit about what's your role at the Ingersoll Machine Tools, and we're gonna have another exciting presentation for the folks that are joining us, and the numbers are going very quickly high up. This is day 29 of our special composite series, and today we have a special guest, the engineer Chris Chaya from Ingersoll Machine Tools. Chris, introduce yourself to us.
Sure. So you got my name right. That's a good start. Chris Chaya. I'm the lead process engineer at Ingersoll Machine Tools. I've been there for about 9.5 years. I just celebrated 9 years in January. Right from the get-go, I came in as Composites. So Ingersoll will kind of show you a little bit about what Ingersoll does here in a minute. We kind of span different industries, metallics and composite, additive and subtractive. So I came in directly into the composites, the additive world through our AFP machines, our ATL machines. From there, I've been the lead engineer on our automated inspection system, which we'll also touch on a little bit here. And more recently, in the last few years, on our large scale 3D printing, and then also our continuous filament 3D printing.
All right, this is awesome, Chris. So we do have a nice presentation gearing up for today. I just want to thank you so much for joining us. As you see, I've put myself in Ingersoll colors. That's a shirt that I got as a gift from Lodo a couple of years ago. For some time, it stopped fitting, but apparently now it's fitting back again when I tried it this morning. So this is good news somehow. And I wanted to give a shout out to Lodo. All right, so let's go ahead and get started with our discussion and our presentation. So I'm going to switch over and see the slides. So I guess we want to get started with what is the Ingersoll tradition and where are you guys located at, and introduction of the company.
Sure. Yeah. So Ingersoll has been around for a long time. This is a shot of our aerial view of our facility. So all the big buildings you see there, that's all Ingersoll campus. The golf course just behind the building is actually the Ingersoll golf course as well. That was founded in 1899, the golf course. Even all the houses around there were basically built to house Ingersoll employees as the company was revving up. So it was founded actually in Rockford. So where we are right now is in Rockford, Illinois. And we've been there since 1891, I believe. For a short period of time, we were actually in Ohio. And then they moved the company to Rockford, Illinois, because of its natural beauty, and it already had some tradition for fine craftsmanship, actually for like building pianos and furniture and things like that. So there was a workforce already available that the original founders basically built on and used to start building machine tools. And we started pretty quickly getting into very large scale machines. By 1906, we had already built the largest milling machine of the day at about 400,000 pounds. And we still continue that to this day, just building really unique, really large machines.
All right, this is awesome. So I'm trying to situate myself. When is this like? So this is the engineering building. I'm trying to remember where is it. I've had long walks in Ingersoll, like, and it's been crazy. But I'm trying to. I can't situate where is the entrance. Is it in here next to the engineering?
Yeah, basically. So that that little arrow on the engineering is kind of pointing towards the entrance. It's kind of between the arrow point on the development center and the engineering arrow point. Right on that edge of the building is the main entrance.
Okay, I situated myself. It's
and despite the size, it's surprisingly not big enough. I know you said you've gone through lots of walks through there, but we're actually in the process right now of expanding. We built the DKIS telescope that recently came online and started taking some pictures of the sun for us, which is really interesting. We built a framework for that, and now we have another contract for the Large Magellan Telescope, which is essentially we're putting an extension onto our building to satisfy that contract.
You know, if I knew you were going to mention this, I actually took a picture with it during the build and during one of my visits. I would have prepared to show it because this has been, it's gigantic. Like when I walk into your facility, the machines, I mean, they are just gigantic, and
it really is. There's so much cool stuff going on there. But this is a composite show, so I tried to stick mostly to composites, and even in that world, I had to kind of narrow it down to just, you know, maybe bits and pieces, kind of the highlights of what we do.
I perfectly understand that. So this is a little bit your tradition. So you're talking about this. Your tradition comes from the milling world, right?
Yeah. So that's kind of where we started, building the largest, most complex, most capable milling machine. So the machine on the left there is actually one of the machines that's permanently housed at our facility. We do some contract work as well. So that machine stays in Rockford, Illinois. And if you get a sense of scale, there's actually a little guy down there.
Yes, I wanted to tell you, like for everyone watching this, and all right, Chris, there's tons of people saying good morning to you. So
Hey, good morning, everybody.
So just to get a scale of this for people who are looking at this, I'm going to maximize the screen so that you can see it on like larger scale, and look at the person in here. So that is the person. This is the size of the machine, and how gigantic is that? And this is the person in the machine. So this is a pretty much impressive. All right, so
and that's not necessarily the largest. We've built bigger machines than that: 5-axis, 6-axis, 7-axis, 8-axis, and we take basically all of that tradition and we apply it towards our AFP machines as well.
So the terminology axis for those of you listening to us has to do with degrees of freedom. So the added degree of freedom, this adds an axis for a machine, and it's not like linear. If you add in complexity, if you add a degree of freedom, you're suddenly tripling, if not exponentially, doing the complexity. All right, so this is a composites show. That's good. We started with the tradition at Ingersoll. Talk to us a little bit about the AFP Evolution, and of course we have a couple of cool videos that are prepared. But what is it that we're seeing in here on the left and on the right?
Sure. So these are some of the original Ingersoll AFP machines. We kind of got into the large scale AFP space as soon as it was available. So the machine on the left is an Airbus machine, and the machine on the right is in Alania. So Alania is one of our largest production sites. We have 7 machines that are producing the 787 fuselages out there in Alania. Those machines at Alania are 32 by 1/2 inch toe AFP machines, just producing all the time 787s.
Yeah, I wanted to tell you the left one looks like an Airbus machine because they do have their manufacturing process a little bit different, whereas Boeing has chopped their aircraft like into sections of barrels. Airbus, they have like these different. It's a different joining process for them.
Yep.
But going from that, I'm just like trying to brainstorm for the world of AFP. Is it like which one would you recommend? Do you prefer not having hoops, not having these circular patterns versus having these joints, or like from an AFP perspective? I mean, both of them, they are design-wise. This is not what we're assessing a design. I'm assessing from a manufacturing perspective. Which one do you think it would be easier?
Easier. I think they're about the same. I think the machine complexity ramps up a little bit with the barrels, with the headstock, tailstocks, because you have additional axes there. But it also allows you to go a little bit faster because you're not, so on the machine on the left, basically you have your XYZ axes that dictate how fast the machine can lay up. On the right-hand side, you could take advantage of that rotisserie in front. So you could kind of combine your XYZ linear feed rate with the rotisserie feed rate. So you could actually, using that sort of setup, you can go beyond the capabilities of just the linear axes.
Yeah, I totally see that. And I was also thinking of programming. I don't know if this is a very quick assessment from my side, but I feel like the programming of parts that don't have these hoop elements will be a little bit easier than the other parts. But I guess it has to do with different. There is multiple of reasons why you make a design a certain way or the other way around. So, right. What is it that we're looking at in here? So we're looking an up close picture on the creel on the head supported type of mechanisms, and then the other side we're looking into. So tell us a little bit, what is it that we're seeing here?
Sure. So this would be kind of what we consider the next step in that AFP evolution. Those original machines had the creel house housed off of the head, kind of far away. That was the way it was done originally. And this is when we introduced our Mongoose module. So we basically shrunk down that creel house and we brought it closer to the head, but still allowing a lot of flexibility. This has been kind of Ingersoll's niche for a while. I'm biased, but I think we truly make the most flexible, capable AFP machine. So, and this Mongoose module was a large part of that. We still have the ability to refrigerate and control humidity in that creel, but we bring it close to the head and we reduce the contact points of the toe path.
So let me ask you a question. So you're saying modularity. Does this mean, like, I can imagine, and if I recall my memory, the answer is yes, but I'm going to go ahead and ask it to you. The head can be deposited and you can pick another head and continue the layup while the operators are like refurnishing the head with material and so on.
Yeah, absolutely. So the image that you're looking at there on the left was our first Mongoose. So that one is not modular. That's a fixed creel. But the one on the right is actually one of our more recent machines. And that machine, there's an image of it a little bit later. That machine has several different end effectors, and they all can be picked up and dropped off automatically. So it has 2 different AFP modules, both 24 by 1/4 for redundancy. It has a tape laying module, and then it has an inverted robotic module that itself can pick up and drop off an inspection system and an ultrasonic knife.
So sometimes I do have questions. There are tons of people saying that these are impressive, huge machines. I have a question. What is the porosity content in the cured composite from the AFP process? I don't think this is really like relevant to what we presented, but if you want to take a stab at this question from Kumar.
I mean, it's kind of hard to answer. I think it really depends on your process and the material that you're using. Definitely, we want to be below that 1% level. I think for most of our kind of thermoset layout processes, but it can vary dramatically, right? And your process can adjust to account for that different porosity levels that you get raw coming out of the AFP process.
All right, this is awesome. Thank you so much, Chris, for responding to that. And let's go ahead and move on in the AFP evolution. So, okay, is that the machine that you can actually go even all the way, you can be manufacturing in the center and also on one of the sides?
Right. So this is actually a pulled out view of the machine that was on the right in the last image. So this has the two different AFP modules, the tape laying module, and an inverted robotic module that can pick up the inspection system and ultrasonic knife. This is, as far as I know, I'm pretty sure the largest gantry AFP machine in the world right now. We beat our own record when we made this one. It's 9 meters between the columns there, and it's 14.5 meters of total wide travel. So what the modules can do is they can actually go outside of that portal. So off to the left, there's a cantilever on the y-axis. So we can move outside of the portal and lay up on a headstock, tailstock outside of the gantry.
This is impressive. Where is this located right now? Are you allowed to say that?
No.
Okay, good. So that's a fair answer. So for everyone tuning in, this is a broadcast with Ingersoll Machine Tools. We're talking with Chris Chaya. And so I know I've been using LinkedIn for a month and I see the LinkedIn feedback and it's working perfectly. This is one of the few times where I try to broadcast simultaneously onto 4 channels, and this is what's happening right now. So on Twitter, YouTube, LinkedIn, and Facebook. And I'm on a new system, which makes it that I'm seeing within the system the Facebook interaction. And that's very, very interesting. So if you're on Facebook and you want to go ahead and post a comment, go ahead or a question, go ahead and do it. I have a method where I can put it on the screen in case we want to tackle that question. So it seems like, Chris, technology is on our side today.
Okay,
all right.
good.
So talk to us a little bit about this slide. And I can see in here the usage of the robotic arms as well as inverted processes. I mean, this looks like you guys have inverted. The tool is held by the mechanism that has the flexibility and the head is stationary.
Right.
So talk to us a little bit about this. And I have a question myself, like why would we be interested in inverting the process?
Sure. So, I mean, as you've seen, we make really large gantries, but we understand that there's a need also for smaller AFP systems, what we would call kind of our mid-level or entry range for AFP purposes, or if you're manufacturing smaller parts and you don't need a very large gantry. We do offer these robotic systems. There are some trade-offs there. A robot is just generally not going to be as accurate as a gantry, especially not the kind of gantries that we do in the history that we have and getting this, the kind of accuracy that we're able to achieve on those gantries. But it has its place. It's less expensive, and it can be versatile and fast. So on the left-hand side, there is what we would call our direct robotic fiber placement system. So that's where you have the creel housed on as the end effector on the robot. And then on the right is what we call our inverted system, where, as you mentioned, it's holding the tool and the creel is stationary. The system on the right there is laying up currently a CDS, so just a calibration plate that we have, but it's really designed for complex shapes in fan blades, composite fan blades. So that's a relatively small part, and having an inverted system like that, it's extremely fast, and it allows you to have modularity without changing end effectors. So in this case, we have the CDS right now is facing the fiber placement module, completely stationary, completely fixed tow path, so very, very reliable. And then it can rotate at the 45-degree angle. That's where we have our ultrasonic knife module. So the robot can basically just turn 45 degrees and access the ultrasonic knife, and then it can rotate fully to 90 degrees, and we have an automated inspection system there. That's our access system.
So let me I'm gonna get up close a little bit to the slide so that people can see that, and I'm gonna be moving the mouse. So basically, you stated this is a CDS. So CDS stands for circle, diamond, square. This is one of these standard tools that are used for AFP machines. So this is a tool in here. That is the robotic arm. And this is the AFP placement head that is fixed. And then you're saying we rotate 45 degrees. So to this location, you're saying that there is an ultrasonic knife in here where we can do some cutting operations. And then we can rotate 90 degrees here and then have some profilometry-based inspection in this location. Is that accurate?
That is accurate. And then not pictured, but off to the right, there's also a built-in projection system. So I can just basically just by rotating the A1 axis, I can access all of these different modules and functionalities.
That is interesting. I like this. All right, cool. So talking about the AFP Evolution, what is this? What are we seeing in here?
So what you're seeing here is one of the newer products from Ingersoll. This is what we call our Hawk module. So we talked before a little bit about our older creel houses housed off of the head, and then we go to the Mongoose module, and then this is the Hawk module. So what you get here is a very ergonomic, very reliable head, very simple tow path. Everything is all fixed in place. And you gain easy access to all of the spools from a single location. You kind of pay for that to some extent, a little bit in some flexibility of the machine to get into female parts, which is where kind of our roll bend roll kinematic in the Mongoose module is really powerful. But for larger structures that are dominantly male or what we call locally flat, so they don't have a lot of curvature to them, the Hawk module is really a great option.
All right, this is awesome. So looking once again into this, and this is, I'm gonna go ahead and, so do I see in here that you can actually mount, so I'm trying to count as quick as I can, and I cannot count. How many, is this 32? 32?
This is 24 total.
Okay, this is what got me off, 24. That's not really conventional. Is this 24 half an inch, or is this
24? I think this rendering, it could be either one.
Okay.
We can house a 1/4 inch or half-inch spool. You just change out a few head components. It's even modular in that regard. But this one, I believe, is 24 by 1/4 is what it's showing.
Okay, and you would be putting spools from both sides. So am I seeing that correctly? So like from both left and right, and this is where the head of the machine, like this is where the placement mechanism is, and this is where the creel is located from both sides.
Right, correct. And this is obviously just a rendering, but this system is in production. We've sold this system now, so.
All right, awesome.
It's kind of newer news, but it's real.
Hey, you guys heard that first on this special series. So this is where Chris, you can subscribe, press the subscribe button. This is all right. So we're gonna play a video next. Hopefully it works well. So we said we're gonna comment on this, Chris.
So this is a video of our inverted robotic system. So it'll show you just very briefly a little touch on each of the functionalities of the system. So AFP, ultrasonic knife for trimming, and axis for inspection, and then the projecting system. So you see here the robot is doing the AFP process on the it's a little bit choppy for me, but I hope it's coming through for others.
Yeah, it is coming through. It did talking on top of videos on the bandwidth is not super optimal.
Right. So there it just did a profilometric inspection And here we have a projector, which is highlighting one of the defects that the operator can repair. And then a close-up shot of that ultrasonic trimming operation as well.
So you have this video also on YouTube, right?
Yeah, we have quite a few videos on YouTube, and I would invite anybody to go poke around on there and see the kind of cool stuff that we're doing.
So what I will do is I'll take that link from you and I will post it in the comments. I will post it in the comments for that people, like if they just want to click on the link and see that. All right, this was an awesome video. So you mentioned several times access. Also, a couple of days ago, we did like a special AFP inspection thing, and I talked about our research, and we use access like as one of the essence for our research. So talk to us a little bit about access, which is a little bit, if I understand correctly, your baby.
Yeah, to some extent, it is my baby. I could talk for a long time about access. It's generally, I think, automated inspection in AFP is near and dear to my heart. I know it's near and dear to yours as well, so I'm sure we could have a 5-hour conversation right now about automated AFP inspection if we wanted to. But just briefly, yeah, access is, and actually these pictures, I think, with the exception of the one that's showing the defect detection, these pictures were taken at your facility. So that's your the access system mounted on the end of your KR120, scanning one of the tools on your mandrel down there, and then we're projecting on the far right the identification of a splice. So the system is not just detecting defects; it's also identifying defects using machine learning algorithms, and then via that machine learning algorithm, you can allow the system to get smarter and smarter over time, and we've seen that come through. A lot of the defects that we couldn't find in the beginning, we're finding now. Some of the materials are noisy compared to others, and we're much better at now detecting defects in that noisy material. So detection is key because you want to find the defects. Identification is also key because you want to be able to apply different tolerances to those defects. So if I have 100 thou gap tolerance, I need to first identify it as a gap so that I can measure it, see how wide it is, and then say if it's in or out of spec. So basically what this image is doing here is it's showing you some of that defect identification. We're identifying the gaps, we're measuring how wide they are, we're identifying the twist, we're identifying the overlap. But what you could also see is that all of the other gaps, some of the smaller gaps and some of the small overlaps, we're ignoring those. So we're not going to present those to the operator. And the way that we would present these defects to the operator, everything that Access finds is basically dumped into a large database of defects. And then we can pull from that database. So for each ply, we can present essentially a report of the defects that were found on a tablet, which is what you see in the image there. We also have a smartwatch interface, which is basically the same functionality of the tablet, just on a smaller size, smaller screen. So you don't have as much real estate there. So it just shows one defect at a time. And then we also have an augmented reality interface using the Microsoft HoloLens, so you can have completely your hands free. Augmented reality is really interesting. It allows a lot of different capabilities in terms of the sorts of information that you can convey to the operator. It's a really rich depth source of information. But at the same time you pay for that, there's always some sort of give and take in positional accuracy. So whereas with the projector, you can get really sub-millimeter accuracy in where you're projecting the location of these defects, the HoloLens and augmented reality is more of a ballpark, I'd say. It's more like a centimeter accuracy. So it's enough to kind of point you towards that defect so you can go repair it. But if you need to have really precise boundary projection, for example, you're not going to get that from the augmented reality system. Not yet, anyway.
Yeah,
we'll see.
Yeah, this is, so you mentioned several things. One of them, facility. So what Chris was talking about is the McNair Center at the University of South Carolina. This is where I work at. And tomorrow we are actually going to have the finale of the 30 days is going to be with my research team, and we'll see that tomorrow. I do have a question for you from Dr. Al-Najm. The question is, what measurement sensors are being used into the inspection system?
So these are Keon's profilometers. I don't think it's any secret that we're using Keon, so I can go ahead and say that. I think you can actually see it in that image there.
Yeah,
The end of the word Keon's. So we use a profilometric system. We kind of played around with image-based systems, so using kind of standard cameras. But the profilometry we find is so much more rich. You get that height information naturally. You're not going to get hung up by glares and things like that. And then also there's a lot of little details that people don't really think about immediately when they think about automated inspection is basically, what do you do with all that data, right? We talk all the time about this digital thread and maintaining the digital thread. So if I have an automated inspection system and I've taken a bunch of high resolution images, what do I do with all those images? I can't just throw them out, because then I'm basically just throwing out all the data that I've gathered, and my digital thread is slightly severed, if not completely severed. So you really got to think about how do you store that information. And the profilometric system is just, it's so much more svelte in the ability to store data. Having those high-res images really eats up data really fast. It really puts a drain on your processing capabilities. And there's a lot of drawbacks that you have to deal with, different angles and glares and all sorts of ambient lighting issues and things like that. So there's ways to do it, and don't get me wrong, it has its place, but we found basically that the profilometers worked out better for us for what we needed.
Yeah, this is good. I believe that the comprehensive inspection system will need to have different types of profilometry is one of them, of course, thermography. So I think so we have a proposal out there where we actually submitted creating an inspection head, very similar to you have an ATL or an AFP head. The AFP machine would drop the AFP head, would pick the inspection head, and that inspection head has actually profilometry and thermography and vision and all of these different elements. You have data fusion that creates a concert between them. So
yeah, I don't disagree with that. I mean, you bring up a good point, right? Is that every system has its pros and cons. Profilometry has a lot of pros, so that's why we went with it. But one of the cons is it doesn't have the ability to detect color, essentially, right? Everything is based on that height profile. So things that are very thin backing film, typically we could still find it because it doesn't manifest as a completely flat surface. It generally is kind of gnarled or something or folded over. So we could still detect that kind of stuff most of the time. But in this kind of nightmare scenario where you have a perfectly flat backing film that's like half under a toe, a profilometric system is not great at finding that kind of thing. And you mentioned the thermography system, right? A thermography system is great because you can actually see through the top layers. You can start to see defects forming maybe that weren't there initially. So delamination's happening 5 plies down. So I agree that ultimately we're going to want all of these systems in place. But for right now, I think profilometry gets us maybe 90% of the way there, and we're trying to maximize that right now. And already we're getting a 99% defect detection rate with a less than 1% false positive rate on these systems. These are in production. This is not like a dream. This is not R&D. One of the things that always confuses me when people talk about inspection systems is they never mention defect detection rate and false positive rate. Everything's kind of conceptual, and it kind of boggles my mind. I mean, it's an inspection system, right? What do we care about? How good is it at finding defects? And it's like impossible to get those numbers. So I'll state it clearly so everyone knows this is over 99%. We have a full 2929 verification system on this to make sure that we're 9095 compliant, just like any other NDI system. So this is not an R&D system in the lab. This is real production. These things have sold. They're out in the world. They're working.
This is awesome what you said, and what's awesome is you've used so many different terminologies that if someone just joined us and he started watching, let's say from day 25, you can go back to the archive page, and you mentioned so many things like comply, in your sentence there was 10 different keywords for people to really understand the full gist of what we're talking about. And the good thing is, if you just started joining us, go back into the archive page. If you cannot find it, just drop me a message and go back through day one all the way till here, and you will get a big picture. And you were right about something, Chris, is we can talk about this 5 hours because obviously we spent on this chart the most since we started. So
Yeah,
talk to me a little bit about this full modularity. Is this what we're talking about? AFP machines that can drop ahead, pick ahead, and move the operation. And there's something very, very particular I see in here is milling. Why is
yeah.
milling? Why do you put milling in this loop?
So yeah, for a while now, Ingersoll has been driven by this modularity concept. We don't want you to have to purchase a new gantry to have different functionality. So we make all of our modules modular, as it were. So everything from AFP to ATL, inspection, ultrasonic trim, all of these things go along with that additive fiber replacement process. But then we also have kind of a teaser for the next slides here, our large scale 3D printing and our mill heads. So you saw some of our tradition in milling. So we're bringing all of those things together. So in theory, you could basically 3D print a tool. You could mill your surface on the tool, drop off those modules, pick up an AFP module, and then AFP directly onto the tool that you just 3D printed. So we want to leave that option open to anybody that wants to play around with it. In reality, there's some hurdles to get over there because you typically want an AFP in a clean room environment. Milling is inherently not a very clean process. But still, thinking towards the future, we want to make it an option so that whoever comes along in the future and says, no, I have a use case where I do want to do this printing and milling and AFP and automated inspection all on one machine, that it's right there, it's ready to go.
All right, this is awesome. So, and do you have currently, like, I'm asking the question is there somewhere right now outside of Ingersoll someone who has all of these 6 options in place?
All 6 of them on one machine? No one has all of them yet.
All right, I imagine.
So that's an open invitation. If anybody wants to do that, go ahead.
Hold on a second. And if somebody through this video go ahead and ends up getting it, I get a mini AFP machine myself.
You get a finder's fee, maybe.
Yeah. All right, awesome. So I've often stated one of the biggest problems is tooling and the problem of creating tools for AFP machine and rapid tools and cheap tools, especially in the R&D stage where you don't want to make an Invar $500,000 tool and the lack of such equipment. But I did mention that in one of the lectures before, I forgot which one, that you guys have a giant 3D printer. And we're going to be seeing in a little bit of time, like the 3D printing of the boat at Maine University. So talk to us a little bit about Master Print and what is it that we're seeing. And I'm going to maximize the slide so that people can see that.
Sure. So Master Print is our large scale 3D printing machine. Typically, we're printing a thermoplastic resin with some sort of reinforcement material. Most of the time it's going to be carbon fiber, but depending on the application, it could be glass fiber. It could even be a natural fiber like a wood flower. And it really smells good when you print those materials. It smells like a wood shop. So yeah, what you're seeing on the screen there is our Master Print that we have in Rockford. This is, again, a newer product for us. This machine was installed a couple of years ago, commissioned about a year ago, I want to say, maybe not even, maybe half a year ago. But yeah, we have this machine in Rockford, so we welcome everybody to kind of come to us and try it out. We recognize that this is a new process and we're all kind of learning together. So we wanted to have a machine that is really dedicated to doing a lot of this R&D and exposing this technology to the world. Again, you can see there a person for scale. That's your old buddy, Brandon.
Oh, that's Brandon.
He's kind of a short guy, but you can see still for scale. So this machine it's got a 12-meter x-axis. It's got a 2-meter Z, 4 meters between the columns. And what he's standing on, what that's printing on right now, is a vacuum bed. So we basically just roll out an ABS sheet, we suck it down with that vacuum, and that serves as our print bed, so we can print some really, really large structures.
This is awesome. So I'm gonna be testing something. I just threw a Facebook comment just to see how it appears, because I've never seen this before. So I'm gonna go ahead and put it here. Oh, okay. So it appears. I wish it was connected to the LinkedIn comments, because we're having so many questions on LinkedIn. But this appears nice how it appears from. So now we know. I'm gonna go back to some of questions before we move forward. I have 2 questions for you. The first one is, you mentioned additive manufacturing. Is additive manufacturing 3D printing?
Yeah, so basically, it's all in the name. Anything where you're adding material, you're building up a part by adding material, we consider that additive manufacturing. So 3D printing is additive, and a lot of times it kind of owns the additives, the word. When a lot of people say additive, they immediately think 3D printing. But technically, AFP, ATL, that's all additive manufacturing as well.
I completely agree with you. And to highlight this a little bit more, the world of manufacturing is split into 3 families. You have all these deformative, where you're deforming, you're casting, stuff like that. You have the family of subtractive, which, Chris, you showed a little bit earlier, the CNC machine removal and the 5-axis and whatnot, and the world of additive. And the world of additive is, whether it is like in this context, is this FFF? Is this fused filament fabrication, or is this like an injection head? I don't know. Is it a filament that's coming in, or?
No, it's not a filament. It's pellet fed.
Okay, it's pellet fed.
Yep. So we suck up all these pellets in our vacuum system, and then we melt them in our extruder. So it's basically a screw, and then we just place them out layer by layer. Just in a lot of ways, it's very similar to a desktop 3D printer. We're just melting that material. We're placing it layer by layer. Obviously, we have a lot of extra things to consider given the scale that we're printing. We care a lot about the thermal properties of this material and how it kind of evolves over time. CTE is critical, especially when you're dealing with large parts like this. A lot of people in the tooling world, they think about CTE in terms of how much the tool expands and contracts during the cure cycle. But for us, during the manufacturing process, it's just as critical, because the tool we're printing it out hot, and then it's kind of shrinking down as it cools. So we have to come up with some interesting process techniques, and we're working very closely with a lot of material developers to basically deal with all these thermal constraints that we have.
And I have one more question about CT scans. In my experience, CT scans are really post-cure or post-consolidation. Have you ever seen CT scans like in green state?
No, I haven't. It's not a very popular option for ply-by-ply inspection. Like you said, it's usually post-cure.
All right, awesome. So let's talk a little bit more about what we're seeing in here. This is up close to this larger scale 3D printing.
Yeah, so this is kind of medium scale 3D printing actually, but it's some pictures to kind of show that process. So what we're actually printing here is simultaneously we're printing 3 sections of a model, basically a wave pool model for a large tanker. And then we mill it. So in the bottom picture there, on this machine in Rockford, we have, again, that modularity concept, 2 different modules. We have the 3D printing module and the mill module. So the 3D printing module is sitting off in the background there in the stand. And then the mill module is providing that final surface for us. And you can see here, when we're printing, we're actually slicing and printing at a 45-degree angle. This is, again, going back to that CTE thing, is really important for us. If we print purely at a Z level or 0-degree orientation, if we slice only at that Z level, we get a lot of warping, kind of potato chipping as the part peels up off the print bed as it shrinks. Having this 45-degree angle allows us to take better advantage of a smaller cross-sectional area, a smaller total path for that print module to go around. And it also allows us to take some advantage of the anisotropic CTE effects of this material. maybe that's getting into a little bit of the weeds, but that's another really interesting topic.
Yeah,
because we have all of these little fibers. So basically we have these small little 1-2 millimeter length fibers in this material. So as we're melting it down, you might think that those fibers are kind of just randomly oriented, but during the print process, we have laminar flow along the sides of the nozzle and things. So a lot of those fibers actually align in the direction of the bead. So what you end up with is this very interesting and complex anisotropic CTE, so that parts are going to kind of move and expand in different amounts in different directions. And that's another topic of very active research right now, is kind of quantifying that and understanding that process.
And I can imagine this explodes the possibility of applications that you might want to try with such a process.
Yes, lots of research to go on there.
Awesome. So this is an up close picture of the previous slide.
Mm-hmm. So that's basically the top there is the as printed surface. So there you can see the different layers. And then we come back and we mill it so we get a nice flat surface on the bottom there. And typically the sort of surface roughness that we get from our milling application is somewhere between 0.5 and 1 micrometer RA.
All right, the amount of people commenting with words such as amazing, impressive, thank you, and stuff like that, this is awesome. So on behalf of Chris and myself, we thank you for all of these comments. All right, so you're popular, Chris. I'm gonna make sure when I switch to the, so I'm actually gonna take a break after I finish, after I threw myself into this months, but it was amazing. But I'm gonna take a break, and then after that, I'm gonna start like some kind of weekly thing, and I'm definitely gonna have you back in one of these sessions. All right. So what is it that we're seeing in here? This is the largest. This is the printed boat.
Yeah, so these are some of the parts that we've printed in the past, just showing you again the scale of the parts and the strength of these parts. So there's a number of the Ingersoll team there basically sitting on top of this 3D printed part. I don't remember the exact size of this. I want to say it was like 20, 25 feet long.
Hold on a second. I just realized something. This bench that everyone is sitting on, this is a 3D printed part.
Accurate, yes.
Oh, wow.
So yeah, we got a row of people sitting on one side and then another row of people standing on the back side. And because of this 45-degree printing process, that's completely hollow. It's basically a shell. The 45-degree printing process allows us to print vertical walls and horizontal walls without exceeding any sort of overhang constraint. So there's no internal support structure in that part.
Yeah, I had to zoom in the camera because I was looking for you, and now I found you. Here you are.
Yeah, there I am.
This is awesome. And what about the picture at the bottom? This is the 3D printed boat.
Right, so that got us a lot of press. So the machine on the top there is our machine in Rockford. That's currently the second largest 3D printer in the world. The reason it's second is because the one in Maine that we sold is number one. And they printed as part of their kind of revealing of this machine, this 3D printed boat. So that boat is 100% 3D printed. And then they actually, when they were doing their reveal, they had a big PR event, and they had some of the senators there from Maine, and they put them on the boat, and they put the boat into the wave pool and turned on the wave pool. So it was kind of big to do. It was really interesting to see.
Is there a video of when they turned the wave pool somewhere?
I'm sure that there is somewhere. There's a whole, you could just search for, University of Maine Ingersoll 3D printed boat or whatever, pictures and videos. You could see a time lapse of it being printed. Yep, it's really interesting.
I will definitely do that. All right, so what are we seeing in here? Is this the same tool from before or something else?
No, this is a bigger tool. I kind of blurred it out because it's not yet officially released in terms of being able to talk about what it is, but as kind of a teaser, this is by far the world's largest 3D printed part. This is using basically the full range of the machine. It's 12 meters long, just about 2 meters tall. This is absolutely massive. So you could kind of look forward to in the near future some more maybe press releases about what this tool is and what it was used for.
Yeah, I'm not gonna try to take guesses, but it does look like something not very far from wings or something of this kind. But hey, I am not gonna try to take guesses now because
Mhm.
obviously you cannot tell me if I'm right or wrong. So
Right.
now we have the reason why we're gonna host you again, Chris.
Yeah.
All right, so we have a video, and then after that, we're gonna wrap it up, me and you. So let's go ahead and play the video, and you can narrate on top of the video.
Sure. So this video now is showing the 3D printer in Rockford, or master print. So this one is just doing a small demo. In this case, it's just a demo for the video, but this is actually a piece of a larger tool that we printed that was basically a plug for a layup tool.
So this is not an animation. This is okay. This is the real machine.
Yeah, this is a real machine. You see it printing live there.
Can you comment a little bit about delamination? Like usually, so I'm not gonna name which company I'm thinking of or which lab I'm thinking of, but there was a lot of publicity about a certain lab that they did a car. And then if you see the pictures up close and personal, I mean, you see that they are cracking. I mean, it's like,
Yep.
it's like, hey, it looks nice, but if you get a little zoom. So how about the lamination in here? Is this Brandon again?
That is Brandon.
All right.
Shout out to Brandon. So yeah, delamination is definitely a thing that you have to watch out for. It comes back again to those thermal stresses that we leave in the part. So we're printing it hot and then it cools down to room temperature. One of the constraints that Ingersoll put on ourselves when we're building a machine of this scale, some large scale 3D printers, they basically print in an oven. So they could kind of control the way that the part cools down. We really can't do that because our machines are so large. If we put the whole thing in an oven, you would double the price of the machine just for the oven. So we basically gave ourselves the challenge of doing all of this outside of an oven, basically just in an open environment. That room right there is temperature controlled, but it's 70 degrees F. It's not humidity controlled. So you have to be careful about the way that you print things. Different materials are going to play a role with different CTEs. That 45-degree angle again plays a big role in how the options that you leave available for the part to delaminate and warp and shrink. And I would say at this point, it's still kind of a learning process for everybody. We're all still trying to understand exactly what are the limitations of this process, and then how far we can push it. I'm happy to say that we're pushing it further and further all the time. I mean, we're breaking world records all the time to the point that it's just kind of like, oh yeah, we broke another world record last week.
Do you
So
actually
yeah, it's
like Guinness World Record? Like
no.
no?
Turns out you have to pay for those things, and it's not cheap. You gotta, in order to be officially recognized by Guinness, you gotta pay some money. So no, we don't really go down that road, but we have a pretty good idea of what's going on in the world in this space, so we know where we're at.
So I have a question for you, which is relevant to how does this compare to 3D printing of houses and apartment buildings? I mean, like we say, this is the largest printer, but what about like the printing of these massive structures?
Yeah, so that's a good qualifier. We should probably say that it's the largest.
Let's say
I don't know, the thermoplastic 3D printer, polymer, yeah, polymer 3D printer.
Yeah,
They do have large 3D printers for printing houses and stuff. They're using cement or a cement-like material. But yeah, this is the types of materials that we're printing would not work for that process, and that process would not work for the types of tools and products that we're producing with our thermoplastic resins.
All right, I have another question in here that so I'm going to go ahead and read the question, and if it's not clear, I'm going to ask the person to restate it. It's when you place the engine and all the other equipment. So when do you place the engine and all the other equipment during the printing process? I'm not really sure.
So I think they're probably referring to the 3D printed boat and getting the motor on the
Oh,
boat.
yes, yes.
So that takes place after the 3D printing process. And just to be completely upfront, I mean, that boat was to make a splash, basically. It was a PR stunt. You probably wouldn't actually manufacture a boat with this 3D printing process. Typically, we're using it more for tooling, mail plugs, or direct to oven tooling with some of the high temp thermoplastic materials like the PEI, PESU. The boat was more just for the wow effect, but they did actually place a motor on it, and they did put it in a pool, so it could work to some extent. But yeah, typically those add-ons happen after the process.
And I am sure that some of you had thoughts about creating like perhaps a pool from the 3D printing machine and stuff like that too.
Yeah, there's no end to the ideas for what we could print. If anybody's familiar with 3D printing, there's this little kind of standardized thing called a benchy, right? It's actually a little boat, and lots of people have asked us to basically print a life-size benchy and go put it out in Lake Michigan or something. So who knows? Maybe one day we'll do that.
I'm trying to I'm trying to do something because I'm finally having so much flexibility with the system, and it's working great. And I can actually talk with you, surf, and show people things and try to search online. Like you just mentioned Benji, so I'm gonna go ahead and show the picture. I just looked it up online very quickly. So this is what Chris is referring to, and this is
Yeah.
somewhat like, hey, can you print this and verify your process? So this is what Chris was referring to.
Yep. Print a life-size version of that so you could actually go out on it.
That would be too good to be true. So we've been online for almost an hour. This has been very special lecture. Thank you so much. And this has been the first time ever I don't have any technical glitches whatsoever. This has been a seamless, like zero issues. And even
Yeah,
like,
it was really nice. Thank you very much, Rami, for having me. I have to say too, your passion for teaching people about composites is really, it's inspiring. I'm very appreciative of that. And thank you to everybody else for joining and watching, coming to you live from my basement.
yeah, and I'm coming to you live from my kids' music room. Someday I should show that. All right, cool, Chris. I can't thank you enough. I've known you for, I'm gonna perhaps say it wrong, 6 years now or 7 years, and one of the first interesting AFP discussions I've ever had with anyone is with you, and this has been nothing short of fun as a journey. And as we continue doing research and discuss together, this is something that's going to continue. Thank you so much to you, to Ingersoll Machine Tools. And tomorrow is, I have no clue how that happened. I don't know how I even started that thing. And now tomorrow is the last episode. Thank you everyone who've been tuning in. This has been nothing short of just impressive. And Chris, thank you once again. And I'm sure that we will see you soon.
Thank you, Rami.
All right. Thank you so much, everyone, for tuning in. Once again, this was a special show for Ingersoll Machine Tools. And this is our Composites A to Z, our Composites A to Z lecture. Tomorrow, we're wrapping it up with the last day. It's going to be a little bit special. It's not going to be new knowledge in the sense of like a certain fixated topic, but we're going to go through a discussion with my research team, and we will wrap it up. And thank you so much.